So today I'm going to talk about post-quantum cryptography migration. So as you might have heard that Google recently announced a quantum processor called Willow. And also we have heard for several years that IBM is making steady progress towards realization of quantum computing. And also we hear various news from other countries such as China, which claim that they have been moderately successful in developing at least some capability in terms of quantum computing. Now, what is happening in the quantum computing world has a bearing on our security, because much of the cryptography that we use today are dependent on the hardness of a few mathematical problems. And by hardness, we mean that nobody knows a polynomial time algorithm to solve those mathematical problems, such as how to factor a very large integer into its prime components, or how to compute a discrete logarithm of a number in a group. So if those things become polynomial time solvable, then much of the cryptography, especially the public key cryptography, becomes broken. And that is a matter of concern, because we have become so intrinsically dependent on this public key cryptography in our security infrastructure, that without such algorithms, security of those information, theoretic security, or practical security of this algorithms or cryptography, we are in big trouble. So we have to see, what is the progress in terms of quantum computing, and we have to also see what we need to do at this point in time. So some people might think that, well, quantum computing is a little bit far off. Even the latest Willow that Google announced, that has about 123 or so qubits. But in order to be practical, in terms of breaking our asymmetric or public key cryptography, the qubits and the number of qubits required has to be in thousands. But one does not know whether a country is actually developing this quantum computing in some kind of silence, such that it becomes a surprise. So we are always worried about quantum surprise. But even without the possibility of a quantum surprise, we still have to worry about the fact that in about 10 to 20 years, most scientists believe that large scale quantum computing may become available. And what I'm going to talk about now is what we should do right away, and why we should do such things right away, even though these things seem to be rather distant, not necessarily, immediate, barring the possibility of a quantum surprise. So you might have read in the last week that Google announced this Willow chip, which seems to solve a very random problem which has no real practical relevance at a very high speed, which in a classical supercomputer would have taken the age of the universe. That sounds very, very scary, but actually when you read the details, you realize that it's still very far from where we should be worried about in terms of, factorizing very large numbers used in, for example, RSA cryptography, or in terms of doing discrete logarithm problems, which are used for our Diffie-Hellman kind of algorithms. But as you know that, since 2018, 19, etc., multiple different iterations of various claims we are seeing in terms of quantum computing. Majority of the cases, the number of qubits is small, and also in some cases it's a rather noisy qubits, which means that even if you have 1,000 qubits, but actual to do the error corrections because of the inherent noise, the number of effective qubits becomes limited to maybe hundreds, which again is not enough to challenge our cryptography, but which is a progress nonetheless. So we often see these papers coming out of Chinese academia that claims to have done quite well. Even in some cases, they claim to have done quite well in terms of symmetric cryptography, but majority of that might not be rather challenging or rather trustworthy. But that does not mean that we should be resting on our laurels and we should feel safe. There are reasons that we need to worry about these things. And uh, so, uh, now what is the concern about quantum computing? Now, quantum computing, through its ability to superpose, so it is able to actually do multiple computations at the same time. Actually, a large exponential number of computing at the same time, and then through disentanglement, you can actually obtain the final results. So people have shown theoretically such possibilities, and in small scale, such things have been demonstrated. So therefore, quantum computing has the possibility of creating the exponential amount of parallelism that we are unable to do with classical computing, where the amount of parallelism we can obtain is rather limited because of the number of resources required is proportional to the amount of parallelism we can obtain. Now, there has been a number of results in the past that has shown that if quantum computing becomes a reality, then certain things become a little faster. So, Love Grover, one of the computer scientists from India, actually showed that uh, you can actually have a square root time speed up. So, which means that if something takes the time, 2 to the n, then you can actually do a square root of 2 to the n. Square root of 2 to the n would actually still very high, and therefore, if you double the size of n, then you become the same amount of exponentiation as before. So if the security was because to solve a problem you need 2 to the n time, Grover's algorithm will make it 2 to the n divided by 2. But if n becomes double, then it comes back to the same thing. So Grover's algorithm, even though it speeds up some of the exponential algorithms, actually does not pose much of a problem, provided we can increase the key size. What is a problem is Peter Shor's 1994 result, which showed that integer factorization or discrete logarithm, this kind of problems on which form the basis of RSA, which form the basis of Diffie-Hellman or elliptic curve Diffie-Hellman, etc. These things become polynomial time. Now that is a concern because Grover does not give you polynomial time. It just does a square root speed up, whereas these things will give you polynomial time algorithm to solve factorization and solve discrete logarithm, which means that RSA, Diffie-Hellman, etc. will be broken. Now, so now we can say in summary that quantum computing, if it becomes realizable, if it has enough number of clean qubits, then the asymmetric crypto will be broken. Symmetric crypto will not be broken. You have to double the key size to get the same level of security as before. So, so now we have said this. So Shor's algorithm is our major problem, and we'll see RSA, ECC, ECDH, all these algorithms broken if it becomes quantum computing becomes reality, and Grover's algorithm does not really matter a whole lot. It does matter a little bit, but it doesn't matter a whole lot. So even today, NIST has AES 128, okay. Whereas even yesterday, we read that certain governments are now actually making requirements for by 2030 people have to move on from AES to 128 and so on. So we are seeing some caution being taken there, but it is not yet that problematic. Now, you might say that, okay, so you earlier said that the quantum computing will be 10 to 20 years, barring the possibility of a quantum surprise, then why are you scaring us? The reason is that there is one possibility that some nation state or some adversary will be recording our communication, uh, encrypted communication, in which we have used in the session. If you record the entire session, in the beginning of the session, we either used RSA or Diffie-Hellman to establish a key, and then use that key for symmetric encryption for the entire session. Now, if assuming that somebody records the entire session's packet trace, and then when they become successful getting their hands on a quantum computing, suitable quantum computer, they will be able to actually break the initial part of the session. They will they will find the key that was established with Diffie-Hellman, and then the rest of the conversation then becomes simple a matter of decryption with the right key. So this is what is called record now, decrypt later. In national security space, obviously, this is a big concern, because in most cases we want to keep the national secrets for at least 50 years or a couple of generations before we actually even declassify them. So if an adversarial state gets hold of conversation between diplomatic posts and the State Department of a country, then they can actually record it, and then before 50 years or so, when it becomes might be only of historical significance, maybe in 20 years they will be able to decipher it, and this could lead to embarrassment and many other issues. Similarly, for banking and other, lifetime of a person's a bank account, etc., are not necessarily only 20 years. So if there are banking related information leaked in an encrypted form right now, and 20 years from now it is unencrypted by an adversary, it can still be used for various purposes, including personal blackmail, etc. So therefore, record now, decrypt later is a real threat. And that's why we have to actually start moving from the asymmetric cryptography that are likely to be broken by quantum computing, even though quantum computing of today is unable to break it. So there is, in this context, there is Moscas theorem. Moscas theorem basically is illustrated in this diagram. So here you see that y is the time it takes to deploy quantum safe algorithm. So if you now want to move all your RSA and Diffie-Hellman, etc., and replace them with quantum safe versions of key establishment or digital signature algorithms, then and then x is the number of years you want to keep the secret, then x plus y, if x plus y is greater than z, where z is the number of years it will take from now to get a realistic quantum computing, then we are in trouble. That means that at the end of the period z, we will be able to get hold of, decrypt all the information that I want to keep secret, and the period for keeping it secret has yet not passed. So that's the Moscas theorem, and that's what the worry is. So what you should do now is NIST has given NIST and Department of Homeland Security has given a very clear direction to the U.S. federal agencies, and I have seen a very similar type of a document circulated by the Ministry of IT and Electronics in India, I don't know if you have received a copy of it. I'm not sure it has been mandated, but it should be mandated. That is to do quantum preparedness. So this picture kind of illustrates the steps in quantum preparedness. And in the US, this is required to be done by 2030. So 2030 should be the time by which all the crypto that is quantum unsafe has to be replaced by quantum safe crypto. So this entire timeline that you see here has to be done by 2030. So I would suggest a similar timeline for Indian financial sector because of the similar reasoning that the NIST and DHS has given to the US federal agencies. So but in order to do this correctly, you have to first figure out what kind of unsafe crypto are in use in various products that you are using. There are various products which has embedded SSL, TLS. There are various products in which you do initial key establishment, session establishment. You use digital signature. So, so you have to actually create what we call a cryptographic bill of material for all your software and applications in which you actually do any kind of communication, authentication or encryption. Now, so you once you know all the places where this kind of asymmetric crypto is being used in your system, then you have to figure out what are the risks. Now, there may be some software that you will be retiring very soon, and therefore you do not have to do anything about it. Whereas in some software, you may have you know that this is going to be continued, till to 2030 and so on. So you have to figure out what are the risks, for the various places where this crypto is being used. And then you have to figure out how to move to a crypto agile system. So in the past, what have happened is our vendors have provided us software where the crypto is kind of intrinsically, embedded into the software in such a way so that extricating the crypto and replacing it with an alternative algorithm is very difficult or kind of impossible without actually redesigning the entire thing. So now you have to tell the vendors that you have to create this crypto in such a way so that replace this crypto in such a way so that tomorrow, if one of the algorithm that what is been now being claimed as quantum safe turns out to be unsafe, because none of these algorithms that have been standardized now by NIST this year, but for as quantum, as post quantum crypto, are information theoretically proven to be quantum safe. They are quantum safe because they are not. We have not found a way to actually break them with quantum computing, because they are based on uh, things like lattices. So finding the shortest distance on a lattice, or some kind of a perturbation in a lattice, and finding the original position in the lattice and so on. So these kind of problems are not known to be solvable using extreme parallelism that quantum computers afford, but doesn't mean that tomorrow somebody will not have a clever way of using the quantum computers to break them. So right now, the algorithms that NIST has standardized are known to be safe, but they are not provably safe. So therefore, I have to have a crypto agile system such that the crypto that I am going to put in has to be I have to be able to extricate that out and replace that with a new crypto algorithm without much work. Right now, the crypto is so ingrained into the applications. Maybe you have to do a lot of work to actually replace them with the newest algorithms, quantum PQC algorithms. But eventually, you want that to be agile. You want to be replaceable. So then you have now moved to PQC, and this should happen by 2030. Then you have to actually monitor what is happening in the crypto space, whether one of the algorithms that you have chosen is being broken, or some news is coming that it is being broken, that kind of stuff, and you have to continue to replace. So you have to continue to monitor the situation. Now, the other issue that you will find problematic now is that the public key cryptography depends on the certificates, digital certificates that we purchase from the certification authorities, and these digital certificates are actually embed in them the algorithms for negotiation of the key, etc. So usually it has a list of algorithms. Most of them are like Diffie-Hellman and RSA and of various key strengths and various things, and also the digital signature algorithm. Now, if we now replace digital signature algorithm and the asymmetric key algorithms in our system, then obviously the two ends will have to negotiate those algorithms, and that means that the quantum post-quantum algorithms must be also part of the PKI certificates, the digital certificates. And this the digital certificate system, the system of hierarchical system of certification authorities, etc., have been developed in last 20, 30 years. So it will take another maybe 10 years or so to actually settle with the new algorithms, embedded into these certificates and so on. So this will take some time, and we have to now put the new key encapsulation algorithm. We have to put the new signature algorithm and so on. So now coming to what NIST has done in 2024. So NIST actually has started working on this post-quantum cryptography standardization effort in 2015. So they first did a workshop where they discussed the upcoming issues that one might face in case quantum computing becomes a reality. Then they announced a competition where various research groups and organizations, they actually could submit their proposal for asymmetric crypto and signatures algorithms which are not dependent on prime factorization or not dependent on discrete logarithm problem. And they received in 2017 they received 82 submissions, of which initial preliminary filtering, they actually accepted 69 of them. And then they did a lot of studies. They gave contracts to various universities to study these algorithms. And then they filtered it down to 26 algorithms as to go to the second round of the competition. Then once this happens, then the groups that originally proposed these 26 algorithms, they have to start implementing these algorithms both in hardware and software, do various kinds of tests, do side channel analysis and so on. And then eventually in 2020, through the submissions of these implementations, testing on the implementation and so on, they actually announced 7 finalists and 8 alternate algorithms for the third round. And in 2022, they actually announced 4 finalists. In the meantime, some of the algorithms that were originally there in the second round, some of them were broken actually, and then they're shown to be actually, attacks exist and so on. And then they in the 4 finalists, they had 1 key encapsulation algorithm through which the keys can be exchanged, and then the 3 digital signature. And in 2022, 4th round started, further analysis, further side channel analysis, and so on. And finally, they had a deadline for additional digital signature scheme. And then 2024 was the time earlier this year when they announced the 3 algorithms. One is Crystal Kyber, which is a key encapsulation algorithm, and Crystal dilithium, which is a signature algorithm, and also they have the Sphinx Plus, which is also a signature algorithm. First 2 are based on lattice problems, which are known to be hard problems and bad for parallelization. Therefore, probably quantum resistant, but not provably quantum resistant, but so far quantum resistant. And then the other one is a stateless hash algorithm. It doesn't matter what the algorithms are. Now there are implementations now available, but question is which implementation is safe, because as we know that algorithms, when they are implemented, implementation may have problems. Everybody remembers OpenSSH fiasco in 2014 when people found, or 2013 when people found very silly problem in the OpenSSH, which led to huge amount of replacement of patching of the OpenSSH library. So crypto algorithms, theoretical provability is not there yet, but bigger question is the implementation has to be side channel free and all that. So that effort is going on, and there are, for example, in India, under the quantum mission announced by DST, there are a couple of groups, including one at IIT Kanpur, who are implementing some of these algorithms both in hardware and software, and they will be testing the side channels and all that stuff. So very soon, some algorithmic implementation of this standardized PQC algorithms will be available. That doesn't close the door on the possibility of India having to implement or announce its own standards for post-quantum crypto, bypassing the ones that NIST has done, or a possibility that there will be a very Indian version done by Indians, tested by Indians, proven, not proven, but highly validated by Indians, which can be better trusted by Indian organizations. That is a possibility, and hopefully through the quantum mission, some of that will happen. But in what the main point that I'm trying to make here, since here a lot of our honorable cybersecurity experts are present in this conclave, that one has to consider this very seriously. I recently had a chance to interview some CISOs for a position at some place. And when I asked them, they were from BFSI sector. When I asked them what their post-quantum strategy was, most of them said they had none, which scared me. And that's why I suggested to Mr. Giridhar for giving me a chance to speak about post-quantum migration and planning the post-quantum migration. And I hope that government will, or RBI and other regulators will soon make it a mandatory requirements to actually plan the migration and provide a timeline by which the migration has to be concluded. So that is all I have, and I will be happy to take any questions if there is any. Thank you.